Let me get started. I'll begin with a word of prayer, hopefully without coughing. Dear Father, we thank you for this day again. I thank you for this class and these students. Just ask that you'd bless our work today, Lord. Help us to glorify you, what we do. In your name I pray, Lord Jesus. Amen. All right, so let me just get straight into it here. So the next story arc of the course is, well, there's a variety of different things that go on, but one of the central sort of themes of this part of the course is we are tending towards looking at things which are more difficult to do by hand and kind of more naturally lend themselves to computer assistance. I would say that's kind of a theme. That said, there is definitely a subset of problems here that are still, like testable. So there will be a in-class assessment of the calculational methods and stuff. I will be emphasizing more like using technology to help us in this part of the course, but don't misconstrue that as like a license to like not figure out how to do things, because you will need to know how to do kind of baby versions of some of the things we'll be doing for the final, something like that. And anyway, let's get into it. So today I'm talking at least a little bit about the real spectral theorem. And let's see here, quadratic forms. So first of all, what's the real spectral theorem? I think I've stated this before, but let me state it again, and this is the theorem. Theorem, if A transpose is equal to A, all right, and this is, in other words, it's a real symmetric matrix, okay? Then A is orthonormally, I don't know if that's two L's or one. I'm going to put two L's. I don't know. Orthonormally diagonalizable. It's a mouthful. The orthonormally diagonalizable. In other words, that is to say that there exists an eigenbasis of orthogonal and normal vectors. Let's say beta, such that beta transpose A beta is equal to lambda 1, lambda 2, lambda n. Right? And here we have the condition that beta transpose beta is equal to the identity. That is exactly the matrix statement. Like, this is totally interchangeable with the statement that vi dot vj is equal to the Kronecker delta ij. So that simple dot product equation here, where I'm suggesting that beta is beta is equal to v1, v2, vn, right? That's a subset of Rn. So you have this subset of n vectors. They're pairwise perpendicular. They all have dot product of themselves equal to 1, which means they all have length 1. That's tantamount to saying if you glue them together into a matrix, the transpose of that matrix times the matrix again gives us the identity, which is to say that the inverse is what? This is equivalent to what? The condition that the inverse of this matrix is equal to its transpose, right? And I'm relatively sure those are equivalents. Any questions so far? We've seen this play out in examples, right? A symmetric matrix has really nice eigenvectors in this regard. This is not an if and only if thing. the criteria to make this an if and only if is a little bit more subtle, and that's kind of more of a 321 thing. I don't think we need that in this course, so I'm leaving that away. Something called normality. And there's a complex analog of this thing as well. That's why this is the real spectral theorem. Okay? Now, so our principal application for today is quadratic forms. What's a quadratic form? So Q, a mapping, let's say from Rn to R, is a quadratic form. If there exists, let's say, A in Rn by n with A transpose equals to A, and Q of V, or I find Q of V is equal to V transpose AV. In this context, what do we say? In this context, typically say that the matrix of Q is equal to A. All right? And there shouldn't really be any danger of confusion here because a quadratic form and a linear transformation are very different things. All right? Do you see the difference between a linear transformation and a quadratic form? Like, is a quadratic form linear? I mean, check this out. So if I have like Q of V plus W, what do you get? V plus W transpose times its matrix times V plus W, right? If you put in a constant times V, what do you get? You get a constant times V transpose times A, then the constant times V again, right? And I mean, it's fairly easy to see that this is like, V transpose AV plus W transpose AW plus stuff, okay? Those two things are what you want. That's Q of V and Q of W, but there's more, right? Because when you distribute this, you've got like the WV and the VW, right? So the stuff is actually Q of V plus Q of W, and then plus, these things over here, when you multiply those out, like when I got W transpose AV, this is not equal to Q of anything. I don't think. I mean, can you find something to put into Q to make it equal to that? I can't. Not without some peculiarity of a particular example. And a constant, well, if I pull a constant, I get C squared. See that? I get two C's, and two C's that's not the homogeneous property that we want for a linear transformation, right? So quadratic forms are not linear transformations, despite the fact that they've got a matrix, right? So this is another use of a matrix. So example one, get over here. Example one, suppose we got Q of x, y, z, fine, Q of x, y, equal to x squared plus 4xy plus y squared. There's my example one. My example two, Q of x, y, z equals to x cubed, oh my bad, x squared plus 2y squared plus 3z squared plus, xy plus 6xz. There we go. Example 3, let's do Q of, excuse me, Q of x1 through xn equal to x1 squared plus x2 squared plus xn squared. So here's three examples of quadratic forms. The third one maybe is familiar to you guys. I don't know. Maybe, maybe not. Can you recognize what it is? What's the third one? The first shall be last. The last shall be first. Here, how about this? Hey, this is nothing more than x1, x2, xn, right? Dot product with x1, x2, xn, right? In other words, this one, and I think this kind of explicit example makes it more clear why we're calling these quadratic forms, right? It's a sum of quadratic terms. That's why it's a quadratic form. Okay? But that's exactly the dot product of x with itself, right? This is just x dot x, right? So if you use your imagination, you can see that this is x transpose times x. And if you have a better imagination still, you could say that that's x transpose times the identity matrix times x. So here, the matrix of Q is the already diagonalized matrix I. There's no need for eigen chicanery here, you know? It's just, it is what it is. Now, so you guys help me out. What's the matrix of this one? So you guys fill in the blank for me. I hope that I've given you guys homework problems like that. I bet I have. Excuse me. So can you guys help me out? What goes there? See, these problems very well could have been introduced to you guys, you know, when we were doing matrix multiplication, because that's all that's really going on here. This is a question of matrix multiplication, you know. Anybody figure it out? One, two, three. That's because there's a 1 here, a 2 there, a 3 there, right? How about this one? One's on the diagonal, right? Now you might be like, well, okay, so what you do, let me just tell you the algorithm. You just pick this term and you half it and put half of it both spots. Because the reason, why would you want your matrix to be symmetric? What would the advantage in that be? If we make, my point is like that you could also, I mean, you could try this out, guys. This is also equal to like xy 1, 4, 0, 1. I'm pretty sure if you multiply that out, you'll also get the formula. But this is dumb. Why is it dumb? Like if I had eigenvectors, right? If I had eigenvectors and eigenvalues, I could write this as lambda 1, you know, let's say x bar squared plus lambda 2 y bar squared. You know? If I had eigenvectors and eigenvalues, I could write this as lambda 1 x bar squared plus lambda 2 y bar squared plus lambda 3 z bar squared. If I'm using x bar y bar and x bar y bar z bar as eigen coordinates. How do I know they exist here? It's the real spectral theorem. The real spectral theorem says that there's an eigenbasis, right? And like the calculation for that is just this. You've got Q of V is equal to V transpose AV, right? So if I just, you know, rewrite that as V transpose, let us say beta transpose A, beta transpose V. We can do this. Why? Beta transpose the identity. Very good. And then check it out. That's beta V transpose times this matrix, which I'll call D, right? And then this one over here, beta transpose B. Well, what is beta transpose V? So you're looking at V in the beta coordinate system times the diagonalization of A, lambda 1, lambda 2, lambda n, times the coordinate vector of v in the beta basis again. Because beta transpose times v is beta inverse times v, right? So like v beta is equal to, hey, most of you guys got this one right on the test, by the way. Like, that was a welcome change. So many times I have that question, and the class just stinks it up, but not the case for you guys. So that's good. Define the coordinate vector of the problem. Anyway, so what is that? Well, if you let v sub beta be x bar 1, x bar 2, and so forth and so on, multiply this out, what you've got is lambda 1 x bar 1 squared plus lambda 2 x bar 2 squared plus dot 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 plus lambda n x bar n squared. Which is why I'm writing what I wrote over there. This is a general result. If we choose the matrix to be symmetric, if we recast the formula for the quadratic form into an eigencoordinate, in eigencoordinates, the formula for the quadratic form is really, really simple. And you can answer all kinds of questions about the nature of the quadratic form if you can do this, right? Now, why are we interested in quadratic forms anyway? Like, who cares about quadratic forms? What are they good for? Can you guys tell me? So, let me just be geometric here for a second, right? If I asked you, I've got q of xy equals to a constant, right? Let's just make the constant, we can make the constant 1 just for the sake of specificity, all right? If I make it equal to 1, it doesn't have to be 1, it could be some other constant. What if it's equal to 1? What does this look like in eigencoordinates? In eigencoordinates, this looks like lambda 1 squared, excuse me, did I say lambda 1 squared? No, lambda 1 without the square. Lambda 1, there's only one lambda 1, right? So lambda 1, there's two x bar. Lambda 1 x bar squared plus lambda 2 y bar squared equals to 1. Now I ask you, what is this equation? What is this equation? Can you tell me? You should know this. Some of you had calculus 2 with Sprano, I think. Am I wrong? What does he spend like a day on? He's got a cute PowerPoint with spaghetti sticks and junk. Did he ever show that to you guys? The conic section PowerPoint? He's not showing the conic section PowerPoint anymore? What is this world coming to? Man, he's got this illustration of hyperbolas and parabolas in terms of these little like sticks getting broken and moved around and junk. Nope. All right, well, I'm going to have to talk to him. I'm trying to share an experience that you guys haven't shared. Sad. So depending on what these eigenvalues are, this is either an ellipse, a hyperbola, or what? Could be a circle if the eigenvalues are equal. That's right. So if they're both positive, it's an ellipse or a circle. If they're both negative, what if they're both negative? Well, if they're both negative and I got the 1 here, the answer is nothing, right? You can't have a minus a sum of squares equal to a positive number. That can't work. But if I put back to a constant, right? If I put back to a constant, then fine. If they're both negative, they just multiply both sides by minus, you're back to an ellipse, right? If one's positive and one's negative, we're talking about a hyperbola. Depending on the nature of the signs, it either opens horizontally or vertically. But when I say horizontally or vertically, I'm talking about the eigencoordinates, right? So up here, you might not be able to see the axis of symmetry of the quadratic form, right? But when you change to eigencoordinates, it becomes like this, which makes its form really simple. What if I had q of x, y, z equal to a constant? Like, what's the deal there? Well, again, when you change to eigencoordinates, it becomes simple to understand. And so most of you had calculus 3, so you have studied what this kind of thing is. This kind of thing is a level surface, right? And depending on, if you have all pluses, you're talking about an ellipsoid. If you have a couple pluses and one negative, it's like I think hyperboloids of 1 or 2 sheets. There's another case in here, I think, that'll give you a cone. If you have like one of the eigenvalues is 0, I think. There's all kinds of different shapes in here, and they're all clear if you study it from the perspective of it being diagonalized, right? If I just write down x squared plus 4xy plus y squared equal to 1, and I say, what is that graph? You know? Well, you guys can do it because you can, you can stick it into Desmos, but what if you want to describe it carefully? Like, what is this thing? You know? What is that? See, we can answer that concretely and excellently if we use eigenvalues and eigenvectors to diagonalize it. And then the other thing you could do, so we can look at level curve, we can look at level surface, but there's another game we can play here, right? We could look at like z equal to q of xy, right? So then in eigencoordinates, you're looking at z as like lambda 1 x bar squared plus lambda 2 y bar squared, right? So I'm not saying it's just level curves, I'm not saying it's just level surfaces. I'm saying that anytime you have a quadratic form, you can make the quadratic form become a much easier thing to think about, a diagonalized formula. And you can see things if you do this, right? So like this, if they're both positive, it's a paraboloid, right? If one's positive and one's negative, I think it's a hyperboloid. You know, if they're both negative, it's a paraboloid that opens down, right? And in a future lecture, I'll show you how that actually ties into the theory of multivariate optimization. We'll be able to give a concrete and hopefully useful answer as to how to maximize or minimize a function of several variables. Now, I think I've got some examples I can show you of this. And yeah, so like my section 7.9 has explicit examples of all the things we're just looking at. I'll try to be brief here because I know you guys, we don't start to talk about the computer projects, obviously. Come on. Windows is, why is Windows resuming? Why did Windows ever stop? Stupid Windows. There we go. Alright, there we go. So, so we're kind of skipping around in my notes a bit. Like I wanted to cover this section first because it's kind of got the biggest bang for the buck. And the stuff earlier in my chapter 7, it doesn't really tie into this too much except in the theoretical sense. So like here's that's what I just worked out today. Here's another example. Here's a useful theorem that's almost like a corollary to what I wrote, which is that the quadratic form is like completely fixed by whatever it does to unit vectors. If you think about this, because the quadratic form has that formula, q of cv is equal to c squared q of v. If you know what happens at q of 1, you can figure out what happens anywhere anywhere past that. If you know what happens on the unit vector, then like whatever happens on the unit vector, it just rescales when you're out at x. So we'll use that. That's why I'm talking about it. But anyway, just get to the point here. Here's a picture. Well, I mean, some of these are kind of dumb. This website no longer works. It died in the website I made these pictures on. It died in the apocalypse of was it the Flash apocalypse? I don't know. One of these. It became unsafe, and all of the wonderful math websites became insecure, and they just sunsetted all of them, which is horrible because we used to have really great websites for visualizing stuff, but they're all gone now. Anyway, so that one's not that exciting. Here's what 3x squared looks like. Z equals a 3x squared looks like that. Here is here's a paraboloid, some shells of it. All right. So here is 2x squared plus 2xy plus y squared. You find the eigenvalues are 1 and 3, which means that you can diagonalize it, making that change of coordinates. And when you do such, it becomes q of x bar y bar equal to x bar squared plus 3y bar squared. So if I put z equals to that, it's clearly a paraboloid, right? Another example here, almost the one we just did. That's x plus y squared. So that's going to be a one of the eigenvalues I think was 0. The other one's 2. And so when you look at it, it's exactly a parabolic trough tilted tilted so that one of the directions the trough goes in the eigendirection. And then 4xy is another example. You find the eigenvalues are minus 2 and 2, which means if we looked at z equals q of xy, it would be a hyperboloid. And so here's the change of coordinates I worked out explicitly. It changes to minus 2x bar squared plus 2y bar squared, which means that when you graph it, it's like I said, it's a it's a saddle. It's a saddle. That's what I should say. And here's a more ugly three-dimensional example. There's a quadratic form. Come on. Find the eigencoordinates, find the eigenvalues, change coordinates, it becomes that, which is exactly, when you look at level surfaces of that, you get tilted ellipsoids. So this is the mathematics you need to undo ugly formulas. If it's a quadratic form, you just find the eigenvalues and eigenvectors, and you can do it. So like for us, the example I had today here, oops, let's not look at that. Oh man, now I probably have to edit this. Yeah, no one cares. Rats. Oh yeah, I can do this. Oh no. Laughing is the gateway to coughing. Let's not do that. So you guys remember our favorite website at this point? One of our favorite websites is what? Chegg. You hurt me with that. Doesn't work for my class? Now I'm feeling better. All right. Maybe I should go sell my stuff to Chegg. I could make some money. Actually, they only pay you in lost education, really. Oh, I'm sorry. What am I saying? Chegg is a study site. The CEO said so. But the eigenvector calculator, right? So all we do is go in there, and you guys tell me the matrix. What was it? Let's do the example one was what? 1, 2, 2, 1. So the eigenvalues for that are minus 1 and 3, and there's the eigenvectors. So that means that we can make this one minus 1, we can make that one 3, and the x bar, y bar directions will be in like 1, 1, and 1 minus 1. That's pretty cool. And let's see here, what else? One more, and then we're done. So what's the other one? What's the top row is 1, 2, 3? Oh, I didn't finish it. Oh, come on, guys. Don't let me. I want to leave you hanging. So here's the story. X, y, put it at 0.5. 0.5. The 6xz, we put a 3 here, and 3. There is no yz term, so that puts 0 over here and here. It's a good thing we figured out that I didn't finish that example. Otherwise, I'd have been really annoyed later today when I figured that out. So now tell me the matrix. We got 0, 1, 0.5, 3, okay.
0.5.
Uh-huh.
2, 0.
Uh-huh.
3, 0.
Oops, 3, 0. 0, 3. 3, 0, 3?
Yes. 3, 3.
All right. And so there we go. Oh, I won't even try to write them down, but the eigenvalues are minus 1.21, 2.02, and 5.19-ish. And then there's the eigendirections, right? So this is what I was saying is, this is not a good test question, right? But this is a fine homework problem for this part of the course. And this is what the real world might give you, right? Data might give you something like this because You know, just because you choose a system of coordinates doesn't mean it's the right system of coordinates to really understand your data. Linear algebra will uncover things for you. All right. Well, now I've got the lecture out of my system. I'm sorry it took me longer than I was hoping. I guess you're not surprised. Let us talk about our computer projects. So you guys have any questions about the computer projects? Let me see if anyone sent me an email. What's that? No one's ahead of you guys in line. The floor is yours. Ask away. How about I just open it up and talk about it, since you guys aren't asking questions. Yes. Which project?
Project A.
Okay. What do you know?
Two things. So I think it's problem 6. If you look down, there's a B. Is it supposed to be beta, or?
Nope, that's B.
It's just supposed to be B?
That's just an identity. So like you could put an M there. So if you've got a matrix, if you have e to the m, determinant of e to the m is exponential of the trace of m.
Okay.
Now if you don't want to put the t in, for you guys, like you could just put the t equals to 1 if you want. I wouldn't be bothered by that. But like I said, for each matrix, well, okay, so I mean, I guess the question is what your competitors do, right? Because if your competitors find a way to verify it with a t there, then they'd be doing better than you, right? But I would be full credit happy if you just figure out how to check it for e to the a. I do think that there is some symbolic this and that in MATLAB.
Yeah.
But what's available at the level of symbolic manipulation is far smaller than the, MATLAB is masterful at numerical calculation. So, yeah. This, I said by direct pen and paper calculation, so what do I mean by that? I literally mean just take A and like multiply it by U1. What do you get? What happens when we multiply this by U1, just to get you guys started? Since this is an orthonormal basis, the thing is you don't need to do this calculation. I'm not saying do this calculation 5 times. All right? I'm saying the calculation can be done independent of your construction of the orthonormal basis. You only do one pen and paper calculation here. Just one. I mean, there's more than this, but how does that go? Well, if these are orthonormal, these are dot products. What's un dot u1? It's 0. What's un minus 1 dot u1? It's 0. What's u2 minus u2 dot u1? It's 0. All of this vanishes except for the first term in this context, which gives you u1 transpose u1. But what is this? That's u1 dot u1. What is u1 dot u1 equal to, though? It's equal to the length of u1 squared. But what's the length of u1? Well, you passed it through the Gram-Schmidt algorithm, right? So it's length 1. So the answer here, apparently, is u1. What does that mean that u1 is?
An eigenvector.
It's an eigenvector with eigenvalue 1. And if you can do that, you can do the rest of them. They won't all have eigenvalue 1, obviously. Like I think u2 has eigenvalue, I think 4. Right? un, well, I won't ruin it for you. All right. Let's see, what else can I talk about? So like, I think the one thing here that's probably most mysterious is I asked you to use the Gram-Schmidt algorithm to orthonormalize these sets of vectors. And I haven't taught that yet, and I don't intend to. But you can look it up. And there is a way to take a set of vectors and run the Gram-Schmidt algorithm on it using MATLAB. I don't know what that is. That's for you to find out. That's why this is a team project. All right? Don't wait for me to teach this stuff. Don't wait for me to teach these. I'm not teaching this. This is for you to figure out. You can ask me questions about it. Let me go on to the other projects. Now, and I've authorized the teams that already found it to charge you guys money if you haven't found it. So
It's true.
it's true. Yeah. See, I mean, he sets the price. It's a, it's an open market. So, but I think, in truth, if you go and express sincere admiration for MATLAB, and come to Dr. Wang with a spirit of true curiosity, knowledge will flow from him like an ever-flowing spring. For he knows all these things. I'm sure he knows exactly what these things are. Like, I don't think it's a super complicated thing to do Gram-Schmidt on those. That's not meant to be, and I'm not trying to get you guys to code it, you're already engineers. You don't need to learn to code. Wait, no, I meant, yes, well, yeah. Well, you're not, you're engineers in training, right? Come on. This one here, let's see, what can I tell you about this one? So, I said create a n by n random matrix. You will find this pretty easily, right? There are ways of creating random matrices. And let me just sort of explain to you what's going on here. Is me being lazy, I didn't want to create another batch of examples, so I decided to make you guys create the batch of examples for part of B. What is the nature of this matrix? You have A is equal to M transpose M. What happens when you transpose this thing? You get M transpose transpose, also known as M transpose M, also known as A. So that's nice, because that means that the real spectral theorem applies to your problem, right? At least it does, in as much as numerical instability doesn't make it not symmetric. But well, anyway, let's hope that doesn't come into play. Anyway, the point is that should be a symmetric matrix. So let's just hope it is. The machine epsilon is out there waiting to corrupt perfect symmetry of matrices and spoil things, but this is MATLAB, so it's going to be fine. Find an orthonormal eigenbasis for A. So just because you find an eigenbasis for a symmetric matrix doesn't automatically make it orthonormal. You can find an eigenbasis for a symmetric matrix with a repeated eigenvalue and have the situation where you don't have perpendicular vectors. But the thing is, on such a basis, you can run Gram-Schmidt on it and make it into a orthonormal eigenbasis. That said, I don't think that's actually going to be necessary here. You're doing a random matrix. The likelihood that a random matrix is generated in such a way that it has a repeated eigenvalue, I think is not. My intuition is that's not going to happen. You'll have distinct eigenvalues, so what I'm saying won't be an issue. We talked about this a little bit today, right? What kind of set is defined by X transpose AX equals to 1? It's the set. You could write it in terms of the eigencoordinates. There should be. If you want to look up literature on MATLAB, you should use the keywords matrix exponential. E to the TA is the matrix exponential. That might help you find code there. Excuse me. Here's a hint for problem 2. If you want to create a matrix with determinant 1, one nice way to do it is to start with the identity matrix and do either row operations, just additive row operations, don't change the determinant, That's a nice way to come up with other matrices of determinant 1. But you can also do 2 row swaps, or a row swap and a column swap. Still got a matrix with determinant 1. You can create all kinds of examples from that that are interesting. All right? So there would be my quick hints for problem 2 there. Let's go to project C. Project C, again, Gram-Schmidt algorithm is something you guys got to figure out. You can pay Sam's group if you want. I'm assuming they figured it out. I actually don't know that for sure. I have faith in you guys. You did it. All right. So, was it that hard?
You guys found an online version, right?
Yeah. And you can look for online resources. That's allowed. You can ask Dr. Sprano if you want. That'll be just funny. Because I know he doesn't care or know about these things. For a much more meaningful conversation, you could talk to Dr. Wang, for example. And, but, okay, so here again, so you'll need to find whatever does the matrix exponential. You don't want to, I wouldn't want to code that. That's an infinite series, like we defined it, right? The other thing in here that we haven't, excuse me. Oh, part E. How do you solve? Fun fact, if you've got dx dt equals to ax, if you have x equals to e to the ta times x of 0, this gives you x of t is equal to x of, it gives you x of 0 equals to, anyway, this right here is how to solve the differential equation. If you have the matrix exponential, you just take the matrix exponential, multiply by your initial condition vector. That's the solution. Since you guys in this project are calculating the matrix exponential, it's just a matrix, a column multiplication way to get the solution. I guess you do need to use symbolic MATLAB there, don't you? But hopefully that's not too bad. Or at least hopefully you do better than the other group, right? Because you're just competing against your friends or enemies in here. I don't know how you guys are. Jordan form. All right, so I guess I need to say more about Jordan form and this notation. And I guess I'll have to, I'm going to say that next time. Hopefully I'll find about 10 minutes to talk about the Jordan form issue. Either I'll make a video later today about it for you guys, or I'll sacrifice class time next time. In the time that remains, like a couple minutes, talk to your group. Make an appointment for like when you're going to meet together and stuff, all right? No? Yeah? And I got your test, so I will get you back your test here, yeah.